Hello, my name is Örjan Rökken. This is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. This presentation has been written and designed in cooperation with Robert Biegler, who is also an author of this talk. For questions and comments, you can reach us on these email addresses. In this talk, we will focus on two problems regarding applying signal detection theory to biology. First, what kind of data do we need to confidently apply signal detection theory? Second, we propose a model for sequential sampling and what to do if information is not instantly available. Organisms experience many situations in which different kinds of mistakes, false positives or false negatives, can have very different consequences. Is this a dangerous animal? A false positive, deciding there is danger where there is none, wastes time and energy through avoidance and lost opportunity to forage. A false negative, deciding I am safe when I am not, could result in me being lunch. Signal detection theory offers a tool for analyzing behavior, both inferring decision thresholds and, given enough other data, defining the optimal decision criterion. For example, here we work with two convenient populations with regard to height. Women are the shorter population with a mean height of 166 centimeters. Men are the taller population with a mean height of 178 centimeters. The two populations are conveniently 2 standard deviations away from each other. If you were given a listed height and a last name, and were asked, is this person a man? Where would you set the criterion where anyone shorter is a woman, anyone taller is a man? As long as you get the same rewards for either correct answer, optimizing the number of correct calls is the best strategy. Assuming you start off with the decision threshold at 170 centimeters, it would, in this case, be beneficial to change over to the unbiased threshold. Although some decisions that were true positives turn into false negatives, even more former false positives become true negatives. The trade-off is worth it. Repeating this with even smaller increments and from both sides of the crossover shows that a point where the curves cross is the optimal decision criterion. That crossover does not have to be at the midpoint that is defined as unbiased. Here we show frequency distributions for a case with 4 times as many women as men. Applying the same argument as before, we find that the crossover point again marks the optimal decision criterion, but that point is well to the right of the midpoint. Being reluctant to say yes, meaning the decision criterion is on the right of the midpoint, is called a conservative bias. This also works for when not the frequencies but the payoffs are asymmetric. In this case, if there were equal numbers of men and women, but each correct identification of a woman, saying, no, this is not a man, earns 4 times as much as correctly identifying a man. Making each woman 4 times as important is equivalent to having 4 times as many women. The same would happen if the asymmetry is in the cost of errors. If a false positive has you losing $4, while a false negative has you losing $1. This graphical method of finding the optimal decision criterion also carries through in changes in variance. With greater variance, the intersection point that defines the optimal criterion shifts to more extreme values, both in physical measurement and in terms of d prime, when scaled by the standard deviation. In simple terms, if there is a liberal or conservative bias, decreasing the d prime will amplify the bias. This also illustrates how discerning the difference between two populations is more difficult when the standard deviation is higher. There is an equation that describes the same relationship. We use that equation to illuminate the measurement problem. In one of the scenarios to which signal detection theory has been applied, the evidence offered to support the claim of a liberal decision criterion is that there are about 4 times as many false positives as there are false negatives. There are many different ways of producing these data. Let's start with this base rate and symmetric payoffs. We find 0.4 false positives for every false negative. We have not yet matched the empirical data. We make the payoff asymmetric, letting the false negatives be twice as important as shown in the stippled line. That shifts the optimal decision criterion, but to find the total false positives and false negatives, we still need to stick to the original base rate. We now get 1.18 false positives for every false negative. Closer, but not yet there. When the false negatives are 4.4 times as important as the false positives, we get 4 times as many false positives as false negatives, matching the empirical results. The decision criterion at 0.099 is still slightly conservative though. If we keep repeating this procedure of picking a base rate and a d prime and iteratively adjusting payoff asymmetry and calculating the new decision criterion until we have 4 times as many false positives as false negatives, the results look like this. Each line connects cases with the same d prime ranging from 0.5 to 3. This point, for example, corresponds to a base rate of 16%, a d prime of 0.5, and false positives being 5 times as important as false negatives. This graph shows the results for this base rate 0.085 and a bias of 0.256. That is a combination which, again, needs false negatives to be 5 times as important as the false positives to achieve the 1-to-4 ratio of the total numbers. The stippled line here connects points with the same payoff asymmetry. That payoff asymmetry varies as we go along lines with the same d prime. And here we're seeing that for base rate 0.068, we need false negatives to be 10 times as important as false positives to match the empirical data. In summary, signal detection theory is often evoked to explain what seems like, at first, an overreaction to rare events. Signal detection theory can make sense of this by postulating a payoff asymmetry. Our calculations support this in that we need to make false the false negatives more important than the false positives to match the empirical finding of there being more false positives than false negatives. Nevertheless, over a wide range of base rates, and specifically the range in which strong responses to rare events need explaining, the decision criteria still ends up being conservative as signal detection theory defines them. Measuring only the total number of false positives and false negatives leaves too many degrees of freedom to pin down what is happening. Measuring only the total number of false positives and false negatives leaves too many false. With this, we'll move on to sequential sampling. There are situations in which immediate discrimination is poor, but repeated examination may improve your assessment. For example, there is a snow leopard in plain sight in this picture, not even bothering to duck behind a rock. Your chances of spotting those who would make you lunch improve if you keep sampling. And in case you haven't sampled enough yet, this leopard is inside a yellow circle. And in case you still don't believe me, I'll zoom in a bit. So the next question we aim to investigate is, can we combine signal detection with sequential sampling? More specifically, how much should you sample? Here we start off by this. D prime is the difference in mean divided by common standard deviation. Further, common standard deviation can be divided into true variance and error variance. The error variance would represent errors in measurement. So one way to represent error variance would be this. Error variance equals the measurement variance divided by number of observations. If we insert this into the previous equation, we get this. And we should see that given a situation where d prime is composed of the distance between means over real variance and error variance, the number of samples would effectively increase discernibility, but with a diminishing return. Then, given our interest in the number of samples, we solve for n and get this. If we assume that each sample or each second of looking or listening or sniffing has the same cost, then total cost is proportional to the number of samples or the time invested. As d prime approaches the maximum possible given true variance, the number of extra samples needed for each increment in d prime approaches infinity, and so does the cost. As d prime approaches the maximum given the true variance, the extra number of samples needed for each increment in d prime approaches infinity, and so does the cost. As sampling increases d prime, the total cost of errors, shown here by the shaded area, decreases because there are fewer of them, and the benefit of correct decisions increases because there are more of them. That must be balanced against the increasing cost of sampling. What is the optimum extent of sampling? Here we show the total payoff calculated as the sum of cost of mistakes, benefit of correct decisions, and sampling costs for a few different base rates. The uppermost line for a base rate of 0.01 shows that the maximal payoff is achieved by stopping to sample immediately after the first one. The lowest line for a base rate 0.4, given the parameters in this example, shows a case where it pays to sample a lot. To make the relationship between these maxima and base rates clearer, we plot them as a surface. Then, for each base rate, the optimal sampling corresponds to d prime that provides the maximal payoff. These are shown here by the red line. This graph shows the case of symmetric payoff. To simplify the graph, let's look at only the optima. Here, the optimal d prime is charted across a large range of base rates. In this example, payoff is still symmetrical, though the different lines have different sampling costs. As we see, for sufficiently low and high base rates, it's enough to sample minimally. Investment in further sampling is more often worthwhile for intermediate base rates. Both the range of base rates over which sampling is worthwhile and the optimal investment in sampling increase as sampling cost decreases. Next, we're going to be looking at the optimal d prime for scenarios where payoff is not symmetrical. This is what that graph looks like. Notice the transformation of the curve. Here we see how false negatives being 4 times as important as false positives skews sampling toward lower base rates. Otherwise, the pattern is much the same as before. Here we have 2 primary variations. On one hand, we have the measurement variances of 0.5, 1, and 2. On the other, we have the max d prime of 1 and 2. Finally, as an added check, we have inserted functionally similar values, underlining how the payoff ratio, rather than the absolute numbers, is what is affecting these graphs. The stippled lines have different payoffs than the lines they go through, but with the same 1:4 ratio. The difference between the yellow and the blue line in this case are sampling costs, which dramatically changes optimal d prime. We have looked at 2 primary questions within application of signal detection to biology. First, we explored the amount of information needed and how insufficient information causes unhelpfully high degrees of freedom. First, we explored the amount of information needed and how insufficient information causes unhelpfully high degrees of freedom. Second, we have applied signal detection theory to sequential sampling problems. There are algorithmic level models of sequential sampling that allow speed to be traded off against accuracy, but do not permit estimating optimal trade-offs. Our computational level model does just that by applying basic principles of statistical sampling. Thank you for your time.